God's first words, as given in the Bible, were, "Let there be light." It is with light that our universe begins. For without light, how little we can know. Primitive man, shivering in his cave during the long night, could only wait for the light that would make the world begin again. Lifting in the sky was the circle of light, in itself so bright as to be blinding, but making all that was dark visible. It is not the object itself that we see, for the object was there in the dark, and its presence did not help us. No, it is the light we sense. Light rays strike the objects about us, and from the manner of the reflection, we learn to judge the texture of the object, its distance, its color. The world in all its incredible complexity spreads out before us. Sunlight is a form of energy. In every direction, this flood of energy streams out in tiny waves. Nearly 93 million miles from the sun, the Earth stops a tiny fraction of them, and all the rest pass on to other destinations somewhere. Life, all life, plant and animal alike, depends on the energy streaming out of the sun. Life reacts to the energy that keeps it alive. Plants grow upward to the light. Animals absorb the energy of light and see by its manner of reflection. Even the most simple single-celled microscopic organism, like this amoeba, has a portion of its single cell that is sensitive to light. The euglena, another microscopic single-celled creature, has a patch of pigment that makes light sensing more efficient, but it is still not yet an eye. In more complicated animals, the eyes are special organs, equipped with lenses to concentrate light from a large area into a small point, so that dimmer light can be sensed. This spider has 8 eyes, each sensing light from a different direction. As an object moves across its field of vision, the movement is picked up first by one eye, then another, like a row of individual cameras. An insect has 2 large and bulging compound eyes. Each is made up of thousands of tubes, like tiny soda straws which lead light down to where it can be absorbed. Each little unit sees light or doesn't see light. The insect sees a pattern of light and dark. It cannot make out much detail, but when the pattern changes, something is moving, and that something may be food or an enemy. But of all the eyes in nature, the most versatile are our own. Some animal eyes can see better than ours at long distance. Some can see better in the dark. But none has so exquisite a method for analyzing color and detail, for seeing the world as the great rainbow of wonder it can be. But of even greater importance, behind the human eye is the human brain. And because of his brain, man can learn to make things larger, clearer, brighter, to transcend distance, time, and size in a continuing journey that takes him ever deeper into the unseen world. How did we discover there was more to see? Very likely, nature itself showed the way. Raindrops on leaves magnify the veins beneath, multiply the beauty, and attract the eye. Lenses, similar in shape, could make greater enlargements. Things seen became larger. Things not seen at all became larger too, and could be seen. In the mid-1600s, a Dutch shopkeeper, Anton von Leeuwenhoek, made the grinding of tiny, perfect lenses his hobby. He saw blood circulation. He was the first to observe bacteria and protozoa. At about the same time, Robert Hooke, using a compound microscope, saw holes in cork which he called cells because they reminded him of rooms in a monastery. Later scientists made the amazing discovery that all living things were composed of cells, and that the cells contained the basic elements of life itself. These are the living cells of the Elodea, a common aquarium plant. They are distinctive in size and shape, but in their ability to sustain life, they are similar to the cells of all living things on Earth. From mouse to whale, from daisy to redwood, there is an unsuspected order, and that order, too, is part of the unseen world. With better microscopes, scientists were able to see exactly how cells reproduced and multiplied. Within each cell is a nucleus containing tiny rods called chromosomes. At the precise moment of reproduction, the chromosomes divide lengthwise and move to opposite ends of the cell. The cell is then partitioned off in the middle, with each of the resulting cells containing the same genetic characteristics carried by the chromosomes of the parent cell. These are living human tissue cells, magnified 1,000 times. Around the nucleus is a complex fluid called cytoplasm, in continual motion, carrying with it the materials and energy necessary for the maintenance of life. An adult human being may have as many as 50 trillion cells, making up skin, muscle, bone, every fiber of the human body. There are some forms of life composed of but a single cell. In a drop of pond water, there could be hundreds of these minute organisms. There are amoebas that ooze their bodies through the water, feeding on the even smaller organisms around them. There are organisms with tiny cilia that move about by swimming. There are creatures called vorticella that look like tulips attached to long stems. All are minute but complete fragments of living matter, almost all indistinguishable from one another except with the aid of a lens, but making up a large part of the world in which we live. One of the most beautiful of all of the tiny single-celled creatures is the Echinosphaerium, which under the microscope looks like an animated pincushion. The pins are tiny spikes with which it captures and draws in its food. The Echinosphaerium, like most single-celled creatures, reproduces by fission. It simply divides itself in two. Even the multicellular animals begin life with a single cell. This is a sea urchin, about the size of a lemon, and much more complex than the tiny echinosphaerium. It lays thousands of eggs, each a single cell. Around each egg are the much tinier sperm cells, all seemingly racing for the goal of entering the egg. One makes it. The egg is fertilized, and a membrane forms about it to keep out the other sperm and guard the fertilized egg within. The fertilized egg divides into 2 cells. The 2 cells divide and are 4. 20 divisions are enough to make 1,000,000. The egg becomes a hollow sphere. The sphere dents inward and begins to take on form. The eggs spin as though overwhelmed by their content of life. In the harsh world of the sea, some will be eaten, some destroyed. But some inevitably will hatch into neophytes, the young form of the sea urchin, which, if they survive, will someday contribute to the continuity of a species. To see even more of the unseen world around us, scientists have turned to new ways of looking at the ultra-small. These are the skeletons of radiolaria, fine dust-like particles from the bottom of the sea that look much like talcum powder. Each grain is featureless, indistinguishable from one another. The scanning electron microscope, 1,000 times more powerful than the ordinary light microscope, sends a focused beam of electrons across the radiolaria shells, and the reflected electrons form a magnified picture on a screen like that of a television set. To preserve the images, still photographs can be taken off the screen. Even the most ordinary substances, expanded sufficiently, take on a new cloak of the unfamiliar. This is an aspirin tablet enlarged 2,800 times. A human hair magnified 600 times. A fine phonograph needle becomes a large, blunt cone resting in a stereo groove. Magnify a polished redwood surface 4,000 times, and what had seemed solid becomes a network of fibers. A used needle point is rough and blunted. A blank sheet of fine white writing paper is filled with holes and chambers. The cavity of a tooth, only 200 times magnified, becomes a pit. The rust on a piece of steel appears as huge crystallized blocks. The surface of a cancer cell can be studied with a thoroughness never possible before. Extreme magnification offers new perspective, too. The smoothness of the billiard ball, once expanded to enormous size, shows crevices that are deeper and ridges that are higher than anything we would find in proportion on the face of the Earth. Which means that shrinking the large would change our view too. Shrink our massive planet to the size of a billiard ball, and its mighty mountain ranges become an inconsiderable unevenness that can be neither seen nor felt. All the ruggedness of Earth, once shrunken, would become smoother than the most polished billiard ball. But who says our slide into the small has reached the final narrowing point of nothingness? With another kind of electron microscope, a transmission electron microscope that can enlarge up to 1,000,000 times, even the tiny structural details of the world within a cell become visible. Our vision sinks beyond the cell, down to the molecule itself. We see the virus that can invade and destroy cells. We see nucleic acid, DNA, long chain-like molecules within the chromosomes that contain the key to all life. We can see a molecule, but a large molecule might be made up of 1,000,000 atoms. No one has yet seen the atom, but Erwin Mueller has invented a field ion microscope that produces photographs of bright dots which represent the atoms lined up at the tip of an ultrafine needle point of metal. But how small is small? Even the smallest particles that we can see in detail today are made up of hundreds, thousands, millions of atoms. And there are particles within the atom much smaller than the atom itself. Who knows? Is there an end at all? Or does the slide downward go on forever in ever-decreasing spirals into realms of smallness undreamed of now? And waiting there as our reward may be secrets of the universe men have never even hoped to dream of before. The world of the too small is not the only world we do not see in our casual, unaided inspection of the universe. Entire worlds can be hidden between two instants of time, as well as between two pinpoints of space. We are bound to time. We can see only what the passage of time shows us, and our passage of time leaves much unseen. We see the fact of life, but so often we do not and cannot see the intimate detail of life as it hurries by. Our time-defeating tool is the camera, which can take individual photographs in fleeting fractions of a second, which can split the second into a far greater number of parts than our eyes can. In 1938, Harold Edgerton, a pioneer in high-speed photography, made black and white films at 1,200 frames per second. When run at the normal 24 frames per second, each moment of time is magnified 50-fold. A second takes nearly a minute to pass our eyes. Modern high-speed photography goes much further. and makes a single second stretch to nearly 7 minutes. A baseball crashes through a window pane. The glass moves absently outward, seemingly free of gravity. We turn on the light, and the filament begins to vibrate with energy long before the slow heating has reached the point of glow. In ordinary flight, the wings of a common housefly beat at 175 times per second. But with high-speed photography, the fly hangs almost motionless in flight, the wings slowed to a steady rhythmic beat. Does a balloon explode when it is punctured? No. The point of the dart enters and fills the hole, and the balloon remains intact. It is only when the rubber fabric tears, some instants after the puncture, that the air escapes and the balloon collapses. A cat falls and lands on its feet in a coordinated movement too fast to be seen until high-speed photography comes to our aid. In the animal world, quickness is a means of survival. But what happens with blinding speed in nature is revealed in much greater detail by the high-speed camera. If much in the world around us happens too quickly for us to see, the reverse is also true. When we look at the plant world, we deduce a stillness, an inactivity. We deny it the appearance of motion that the animal world so abundantly possesses. But the camera can take one picture now and another sometime later, and so on. Time is compressed, and the plant world bursts into motion. Even when things are neither too fast nor too slow, we are frequently prisoners of inattention. We don't look about us long enough. We don't look closely enough. So much of the world around us, even when it is there to see, goes virtually unseen. Have you ever looked closely at the small world of insects? There are 850,000 different species, more than all other animal species put together. But for the most part, they are anonymous until a lens reveals an astonishing world of form, structure, and beauty endless in variety. In the small world of living things, there are dramas as huge as anything that happens in the larger world of nature. Outstanding nature photographers like James W. Wilkie capture many of these moments with skill and understanding. A spider makes its web with unconscious artistry, spinning a geometry no Euclid ever taught him. He does it neither to demonstrate a theorem nor to create art. He needs to eat. And the frail beauty of his sticky threads is a deadly trap. The grasshopper that blunders into it cannot free itself, nor is the spider disposed to let it do so. Brutal? No, for animals must eat, and death is part of life. Consider the male Cecropia moth. It is constructed in beauty with strong, colorful wings, with sharp senses. Its antenna can detect the scent of a female moth 1.5 miles away. Yet all its design has one purpose only: reproduction. And he must locate a female quickly, for he has neither mouth nor digestive system. He is marked for quick and inevitable death. In the only act of his moth life, he fertilizes her eggs. And work done, flutters to the ground to die. The female has one more act for her part. Carefully, she must lay her eggs on the leaves that will serve as their food. That done, she too will die. The orphaned eggs each contain enough food to allow the specks of life within them to develop into small, black, furry caterpillars. Their only function in life now is to eat. The female moth has chosen their food supply with unerring instinct. On any other kind of plant, they would starve. The caterpillar grows, and its soft tissues expand against the unyielding cuticle, which must eventually split. The caterpillar crawls out of the broken skin, it molts, and a new and larger cuticle forms. By the 5th molt, the hormonal balance within the caterpillar begins to change its pattern of life. The food reserve it has laid up within will see it through, and it will never eat again. It begins to form thin silk threads of a special protein produced by glands of its own body. It weaves them about itself, establishing a soft white prison, thicker and thicker, returning to a new kind of egg. It is a new kind of egg indeed, for within it, the caterpillar retires from life, becomes still. Within itself, its entire body plan is broken down and rebuilt in an utterly new fashion. The seasons change as the house of silk clings to its branch. Within, undisturbed, the work of rebirth goes on. Spring comes, the work is done. The spark of life brightens and flares. What was once a caterpillar breaks through its cocoon and emerges a caterpillar no longer, but a brilliant Cecropia moth. Pauses on emergence, waiting for its wings to dry and grow strong enough to carry it. The life cycle has come full circle. But what is the purpose of it all? What does it accomplish? In itself, little. But it is not in itself and by itself. It is part of the fabric of life. Insects feed upon plants. They, in turn, are fed upon. One species could not live without the other. Like an intricate maze, lines connect this species to that into a huge single world of life, of which man is a part, of which man is only a part. A large part of our unseen world is hidden from our eyes by physical barriers. We think of water as being transparent, but consider 10 feet, 100 feet, 1,000 feet. 70% of the Earth's surface is covered by ocean, 2 miles deep on the average, 7 miles deep in spots. We can't see through it. We see only the surface. But underneath that surface is a world of life, the original world of life. It was perhaps 3 billion years ago that tiny bits of life first stirred in the ocean. It was only 300 million years ago that the first life forms, primitive insects, spiders, snails, a few stubby-legged fish, dared to venture into the hostile environment of the dry land. Even today, ocean life is predominant. The plants of the world convert the sun's energy into food and change carbon dioxide into life-giving oxygen. Something like 80% of all the food and oxygen used in this way is formed in the ocean. Where are the plants of the ocean? They are there, tiny microscopic pinpoints of life. The plant plankton present in uncounted millions across the surface of the ocean, crowded into the top 100 feet where the sunlight penetrates. Those tiny cells are the grass of the sea on which ultimately all other life in the ocean depends. Under the microscope, these minute plants take on a jewel-like appearance. They are so small that it takes hundreds of them to stretch across a single inch, but enough of them gather in 1 acre of ocean surface to weigh 5 tons. Though the plant plankton are consumed in enormous quantities, their eternally busy division keeps them ever present in endless numbers, the self-renewing grass of the sea. Not all the plankton are microscopic plant cells. Many are tiny animals that feed on the plant plankton around them. Even larger animals add to the plankton in the earlier periods of their lives. Sea creatures are born of microscopic eggs, usually near the surface, where they too must be near their food supply, the tiny plant plankton. When the eggs hatch and the tiny larval creatures emerge, they are themselves a food supply, for the rule in the sea, as on the land, is that the large eat the small, and the small make up for it by multiplying more quickly than the large. The animal life of the sea exists in wild profusion and in wide variety. There are wonders of weird beauty we never see. The water hides them. There are animals that look like plants, sea anemones with stalks and colorful petals. But they are not green. They make no use of sunlight. And the lovely petals are stinging tentacles that entrap other forms of life. There are slug-like creatures called nudibranchs that look like stalks of bananas. They are only 3 inches long, and what look like bananas are a breathing apparatus. There are worms with tufts of feathers like delicate crowns. There are sea creatures with their life substances so thinly spread, they are transparent. There are other creatures simple enough to reproduce merely by budding. First one individual, then another breaks off from its parent. The object of life here is staying alive. Under the pressure of the drive for food, some sophisticated devices come into use. The anglerfish does what its name implies. It has a fishing rod and a lure attached to itself. The lure quivers like a worm. A small fish can be caught by something as primitive as a sea anemone with its poisoned, writhing tentacles, soft but deadly. It can be caught by something as advanced as a larger fish with streamlined shape that sends it piercing through the water and sharp teeth from which there is no escape. A crab flees from an octopus which coils in pursuit. A lobster is caught by a moray eel, whose sinuous body can twist itself into a knot, if that is necessary to hold its prey. A huge ray flaps its oversized dorsal fins like wings and flies through the ocean world like a graceful bird. Some of the largest whales and sharks and the manta ray bypass the normal food cycle of the sea and live entirely on enormous quantities of plankton. The ocean of water is not the only ocean on Earth. We ourselves live at the bottom of another one. It is the ocean of air, our atmosphere, which reaches for 100 miles and more above our heads. Plants shoot pollen or seeds into the air, making use of the wind as a highway to spread life. And with them are the particles sent into the air by man himself. Under the microscope, there is strange beauty and color in the fly ash, soot, and dust that man's uncaring activity pours into the air. Beauty in deadliness, and artistry in death. For our lungs have developed over hundreds of millions of years to deal with relatively clean air. But look higher still, beyond the dust and toward the heights. Water vapor has been drawn up high into the air where it cools and forms clouds of tiny ice crystals. Sometimes the ice particles within a cloud collect, grow larger, and begin to drift downward. If the lower atmosphere is warm enough, they will melt into rain. If it is cold, the collected crystals will remain solid and will fall as snow. Under the microscope, each flake reveals a complex and symmetrical pattern of beauty, a frozen star with 1,000,000 sisters, each with the same six-sided symmetry, but different in detail. It is easy to believe that of all snowflakes ever formed, no two are exactly alike. And beyond the clouds, the vault of heaven, with the bright sun by day, at night the moon, the planets, the stars. For thousands of years, shepherds, travelers, and lovers have watched the night sky, counted the stars, and traced out fanciful pictures among them. No one dreamed they saw so little and left so much, so incredibly much unseen. But the same lenses that can enlarge the small and make a speck of dust into a monolith can, in other arrangements, draw near the distant and make bright the dim. In 1609, the Italian scientist Galileo placed two lenses at opposite ends of a metal tube and pointed it at the heavens. He uncovered an unseen universe, far more vast and marvelous than the new worlds discovered by Columbus a century before. Galileo looked at the moon, and what had been a source of wonder and superstition became a world. It became a panorama of mountains and craters and dark expanses called seas, waterless seas of silence and dust. A strange world without air, without water, without life, brought closer to us, first by better telescopes, and then by more sophisticated rockets, until upon a magic day in July of 1969, men first stood upon a world not their own, and looked back upon a world Galileo couldn't see. Galileo also looked at the sun, protecting his eyes by letting the image flash through the telescope and onto the wall. He saw spots moving slowly along its face. Better instruments have shown us the sun's surface in detail, given us a vision of its marbled heat, and at its edge, against the black of space, the leaping, arching red of its giant flares that lift gouts of ruddy flame as far as 250,000 miles into space. To the naked eye, the planets looked like no more than bright stars. Through Galileo's telescope, these bright dots became recognizable planets. Mars, 35 million miles away at its closest, is a ruddy world with darker areas and with ice caps at either pole. Some astronomers thought they saw straight lines, which they called canals, and dreamed of intelligent life there. But in the 1960s, rockets whizzed close by Mars, took photographs, and revealed an empty world with no canals, little air, and craters as thickly strewn as those upon the moon. Venus is even closer to us than Mars, only 25 million miles away, and shows phases like the moon. Venus is closer than we are to the sun, and its surface temperature is far above the boiling point of water. There is the distant world of Jupiter, 11 times as wide as the Earth, nearly 500 million miles from us, with a great red spot whose nature is still a mystery to us. Saturn, somewhat smaller, nearly twice as distant, looked oddly lopsided in the first telescopes. Improved lenses showed it to be unique, for it had thin, flat rings circling its equator. In all the universe, nothing else like it has yet been seen. Beyond the solar system is the world of stars. Not merely the thousands we can see at best with the unaided eye, but stars by the hundreds of thousands, by the tens of millions, by the billions. 1 million stars in a single globular cluster. 100 billion stars in a single spiral galaxy. Between the stars, clouds of dust and gas, bright like the Orion Nebula when lit by stars within that dust, dark like the Horsehead Nebula when there are no stars within and when the dust and gas block the light of the stars behind. Exploded stars, leaving the wreckage of their substance expanding outward for 1,000 years, as in the Crab Nebula. And all these stars together make up our own spiral-shaped galaxy of 100 billion stars. Looking through the long direction, we see it as the Milky Way. And beyond our own galaxy are other galaxies, billions of others. Farther and farther away lie the objects, millions of light years away, with each light year counting 6 trillion miles. How much farther does the universe stretch? Where does it end? Does it have an end? Or do the stars and the galaxies go on forever? As the world of the small may descend forever in narrowing spirals, does the world of the distant large ascend forever in expanding spirals? Do we stand in the middle, looking each way into endlessness? And will some of the universe always remain unseen in each direction, despite all we can do? We can only wonder and speculate, as we must with much of our world that is yet unseen.